Hello guys, my name is Nikhil Seth. Today I'll be speaking about the project which I have done in Artix-7 board. This is what we call as a Artix-7 board. So I have implemented an FPGA based buzzer system where each button press, like these buttons, plays a different tone. Each button press plays a different tone. So as you can see, these are the buttons and this is a 5-volt piezo buzzer and here are the buzzer inputs. The blue color casing which you see here, this is a protection cover usually put there. You could just remove it and then you could see 3 pins here. The first pin is enable pin, middle there will be source and the last pin is the disable pin. So to run this project, first you have to connect the middle pin to the enable pin here. I will later on show you the hardware also, so don't worry. So now moving on to the Verilog code for this project. So this is a module named buzzer multi-frequency. It has 2 inputs and 1 output. First input is the clock and the second inputs are the 5 buttons. 4 to 0 indicates 5 buttons and the output is the buzzer which we will get the output from. And the PWM counter which we are seeing here, this is a 16-bit counter to track the PWM timing, and the PWM signal here stores the value of the signal state. It tells us that the signal is high or low. The PWM period here, it stores the corresponding period of the selected button. Now moving on to defining the notes here, maybe musical notes. So now I am taking 100 megahertz of clock and these are the frequencies which I'm using: 200 hertz, 500 hertz, 1 kilohertz, 2 kilohertz and 4 kilohertz. The formula which involves here is clock frequency by desired frequency. That means how many cycles it can, how much PWM period it can produce. So here it is 100 megahertz by 200, that is 500,000 PWM period, and so on. Now let us move on to this block. This is the always block which runs on every rising edge of the clock. It uses a case statement to check whether the button is pressed, and if no button is pressed, it goes to this silence period where it does not produce any sound. Now this is the first button, this is the second, this is the third, this is the fourth, and this is fifth. So like this. And now let us move on how the PWM signal is generated. So if a button is pressed, that means if PWM period is not in silent or not in silent mode, then the PWM counter increases, and then it is compared with the PWM counter is then compared with PWM period by 2. So if the PWM counter is less than period by 2, the PWM signal is high, and if the counter is greater than equal to period by 2, then the output is low. So this creates a 50% duty cycle square wave. That means for half of the time period it will be high, and then for the half of the time period it will be low. So creating a square wave kind of thing, and it produces a frequency like that. And then if there is no button pressed, the PWM signal is set to 0 here, then which mutes the buzzer. Okay, then finally we are assigning the buzzer output to the PWM signal which was generated right now, the square signal, square wave. Now moving forward to the RTL analysis. Here is the RTL analysis. If you run it, you will get a schematic like this. Go to the schematic here. This is the RTL analysis which we are seeing right now. There are 2 inputs, the clock and the 5 buttons, and there is the output here. This is buzzer. So now let us talk about this block. This block is PWM frequency selection block. It stores different PWM periods corresponding to button inputs. It allows different frequencies to be selected for the buzzer based on which button is pressed. The inputs are the button and the output is corresponding PWM period value. So now this block is PWM period storage block. So its function is to store the selected PWM period from the ROM. It ensures that PWM period remains stable while the signal is generated. The inputs are D and clock here, and the output is Q, which stores the period value. Now let us talk about this block, PWM counter block. So the this counter increments with each clock cycle to generate the PWM waveform. It is required. This block is required to compare against the PWM period for signal generation. The output here are clock, the D is incremented counter value, and the Q is current counter value. Now we'll talk about RTL add block here. Its function is to increment the PWM counter register value. So it is used to generate a running counter for PWM generation. The previous counter value is I0 15 to 0, and the constant increment value is I1 here, and the output again is the incremented counter value. Now let us move on to RTL NEQ. So its function is to compare the counter with the PWM period. So why is it used? It is used to reset the counter when it reaches its PWM period. Its input are the current counter value here, 31 to 0, and this I1 31 to 0 is stored PWM period value, and the output is 0. So this is the result of the comparison used to reset the counter. Now let us move forward to RTL LT. So here is RTL LT. Its function is to compare the counter value with PWM period. So why is it used? It determines when the signal should be high or low. This is also called PWM signal generation block. Its input are I0 31 to 0 current counter value and I1 31 to 0, which is PWM period value, and the output is 0, so which is the comparison result, 1 if the counter is less than period and 0 if otherwise. Now let us talk about RTL R shift. So RTL R shift is it right shifts the counter value. So it helps generate different duty cycles for PWM modulation. Its input is I0, the counter value 31 to 0, and I1 1 to 0, which is 1 bit 0 1 it shifts by 1 bit, and the output is the 31 to 0 PWM value, which is the shifted value. So now moving forward to the RTL mux here. What does the RTL mux do? It selects between different signal values. So why is it used? It is used to choose the correct PWM signal based on the logical conditions. So if any of the button is selected, it chooses that button, or if not, it goes to the default value, which is low signal. Now let us talk about the RTL REG sync here. So its function is to store the PWM signal, and it is used to synchronize the output signal with the clock to avoid glitches. The inputs here are clock, D is incoming PWM signal, and the RST is the reset signal. Output here is Q, which is the stored PWM signal. And at last, finally, the buzzer output, which receives the final PWM signal from PWM signal reg, which is from here, which determines the frequency and duty cycle of the buzzer sound. Finally, let us move on to the buzzer.xdc file here. So you can get the .xdc file from the source, which will be mentioned. And these are the input ports which you are defining from the which is present in the Artix board there. So this is for the clock signal, and these 5 are for the push buttons, and this is for the buzzer output here. So after writing a Verilog code and then analyzing the RTL analysis and finally writing the buzzer.xdc file, now it is time to run the code. So first we'll run the synthesis, then we'll run the implementation, which is indicated here, and finally we'll generate the bit stream. So generating the bit stream, if you directly click on it, it will automatically run all your synthesis implementation, and then it will finally generate the bit stream also. So now here it is loading here. So after the bit stream is generated, I will show you the output. So after you have generated the bitstream file here, now let us move on to the hardware manager. So from where you will dump the code. This is the hardware manager, and now is the time when you connect the board to your laptop or PC. Now open target, click auto connect here. So let us finally see at the demonstration. These are the 3 pins which I was talking about. Now let us connect the jumper wire here from the source to the enable pin. This is the buzzer, and these are the buttons. Now let us check if our buzzer is working. Yes, so finally it is working. If you press different buttons, you will get different frequencies of sound.